Hello everyone, welcome to JCE Connect. So this is Professor Vinayak Ratan from Department of Mechanical Engineering, Jain College of Engineering, Belgavi.
Hello. In the last class, we have seen the derivation of shape function for beam element in terms of global coordinate. In today's class, we will be deriving shape function for beam element in terms of natural coordinate. So we call it as Hermite shape function. So whenever in the exam it is asked to derive the Hermite shape functions for beam element, you are supposed to derive it in terms of natural coordinate. So we usually know how the natural coordinates are denoted. In x direction it is denoted as xi, in y it is neta, and in z it is zeta. So before we move on to the actual derivation, we'll first convert the shape functions which we have already derived in terms of global coordinate into natural coordinates. Let's see what is the difference. So we know v of x, the last expression, the last derivation, v of x equal to n1, n2, n3, n4, and this is your displacement matrix. These are the transverse displacements and slopes at node 1, and these are the transverse displacements and slopes at node 2. So when you write it in terms of natural coordinates xi, that is v of xi, we get h1, h2, h3 and h4. And here v1 dou v1 upon dou xi, v2 dou v2 upon dou xi, where dou v1 upon dou xi are and dou v2 upon dou xi are nothing but slopes, okay, with respect to v1 and v2. But we need to write, we cannot write here dou v upon dou xi, we need to have theta 1 and theta 2. In order to do that, we need to use the relationship between a global coordinate and natural coordinate. So in general, we'll write here dou v upon dou xi. By using chain rule, we'll get dou v upon dou x into dou x upon dou xi. If you just cancel this dou x, you'll get back again this equation. Now from the relationship between global coordinate and natural coordinate, we know dou x upon dou xi equal to le by 2. When you substitute here, so dou v upon dou xi, you will get it is le by 2 dou v1 upon dou x, and we know from the previous derivation dou v1 upon dou x equal to theta 1, dou v2 upon dou x equal to theta 2. So we'll be getting dou v1 upon dou xi equal to le by 2 theta 1, dou v2 upon dou xi equal to le by 2 theta 2. Now substitute these values in this equation, equation 1. So this is what you will be getting. Okay. Once you get this, multiply these two matrices and you will be getting this one. Okay, h1 v1 plus le by 2 h2 theta 1 plus h3 v2 plus le by 2 h4 theta 2. So again writing this expression in matrix form. So we need to have here displacement matrix. We cannot have this one. Okay, so we will be getting it like this. So in short, we will be writing it like this: v of xi equal to h into q, where h is the Hermite shape function and q is the displacement matrix. Now we will derive the Hermite shape function h1, h2, h3 and h4. So let's start with the main derivation. So Hermite shape functions for beam element. So in order to derive, first let us consider a beam element having two nodes 1 and 2, each node having 2 degrees of freedom as shown here. So that is v1 is the transverse displacement at node 1 and theta 1 is the its slope at node 1, and v2 is the transverse displacement at node 2 and theta 2 its slope. Now since we are deriving it in terms of natural coordinates, we know that the values of natural coordinate vary from +1 to -1. As shown over here in the element, at the center of the element the value of xi is equal to 0, and to the left it is -1, and to the right it's not -1, it is +1. Okay, it's +1. So from the above we know that Hermite shape function is given by h equal to h1 le by 2 h2 h3 le by 2 h4. Now next let's come over here. Now in order to derive the Hermite shape functions h1, h2, h3 and h4, we need to apply boundary conditions. So this table gives you the boundary conditions. In order to properly understand this table, we need to refer this variations of shape functions which was discussed in the earlier class. Now you can see here, in order to derive h1, so these are the boundary conditions which are applied here. So you can see only h1 is equal to 1, as here v1 is equal to 1, rest all three are 0. See, 0, 0, 0 with respect to node 1 and node 2. So you can see only h1 is 1 at node 1 only, and rest all it is 0. In the similar way, you can have here at node 1 this slope of h2 is equal to 1. You can see here at node 1 slope is equal to 1, rest all three values are 0. Then similarly here for h3 at node 2 h3 is equal to 1. You can see here v2 is equal to 1. Okay, and rest all three are 0. And similarly here theta 2 is equal to 1, slope is equal to 1, so slope of h4, that is dou h4 upon dou xi equal to 1, and rest all three values are 0. Okay, so these are the boundary conditions. Using these boundary conditions we will be deriving the Hermite shape function h1, h2, h3 and h4. So let's move. So this is, let us assume interpolation polynomial function for h, which is given as h equal to a0 plus a1 xi plus a2 xi square plus a3 xi cube. Let me call this as equation 1. Why this expression has 4 terms? Since you can see here each node of a BM element has 2 degrees of freedom. So whole element has 4 degrees of freedom. So there should be 4 terms when you assume a polynomial function, and it should be cubic. So this is the equation, and let us call this equation 1. Let us differentiate this equation. When you differentiate this, when you differentiate a0 it will be 0. When you differentiate this you will get a1. When you differentiate this you will get 2a2 xi plus 3a3 xi square. Let me call this as equation 1. Now one by one we will go on obtaining the expressions for h1, h2, h3 and h4. To find h1 we will be applying these boundary conditions at node 1 and at node 2 as you see here. So at node 1 we know xi is equal to -1, h1 will be equal to 1, and dou h1 upon dou xi equal to 0. You can see here above h1 is 1 and dou h1 upon dou xi equal to 0. So when you substitute these values in these two equations, you will be getting a0 minus a1 plus a2 minus a3 equal to 1. Okay, when you substitute these value h1 equal to 1 and xi equal to -1 in this equation 1, you will be getting equation A. And similarly you substitute dou h1 upon dou xi equal to 0 and xi equal to -1 in equation 2, you will get this equation a1 minus 2a2 plus 3a3 equal to 0. Next, similarly at node 2, h1 equal to 0 and dou h1 upon dou xi equal to 0 and xi is equal to +1. You can see here. So these boundary conditions at node 2. Okay. So when you substitute them, you will be getting these two expressions. a naught plus a1 plus a2 plus a3 equal to 0, a1 plus 2a2 plus 3a3 equal to 0. Let me call these equations C and D. What is the next step now? So we need to add these equations a plus c, then b plus d. When you add these two equations, you can see here, when you add equations a and c, you'll be getting, when you add these two, a and then c. So a naught, 2a naught, a1 will get cancelled out, plus 2a2, a3 will get cancelled out, equal to 1. That's what you are getting here. Okay. So you'll be getting a naught plus a2 equal to 1 by 2. Let me call this as equation E. Now add equations B and D. Equations B and D. You add equations B and D, you will be getting this expression A1 plus 3A3 equal to 0. Let me call this equation F. Now when you substitute this equation F in equation B here, in this expression, that is A1 plus 3A3, we know A1 plus 3A3, from here it is 0. When you substitute that, you will be getting minus 2a2 equal to 0, which implies a2 equal to 0. And when you substitute a2 equal to 0 here, over here, you will get a naught as 1 by 2. Okay. Now we will be finding the values of a1 and a3. So from equation C and F, let's see what this is, equation F and this is equation C. Using that, so we know this is the equation C, and from equation F, a1 will be equal to minus 3a3, and we know the values of a0 and a2. Substitute that, you will get a3 as 1 by 4. Once you get that, substitute it in equation F, and then you will get a1. Once you get all these a0, a1, a2 and a3, which are nothing but generalized coordinates, substitute the values of a0, a1, a2, a3 and equation 1. When you substitute that, this is what you will be getting. Take 1 by 4 common. So h1 will be equal to 1 by 4, 2 minus 3 xi plus xi cube. This is the Hermite shape function h1. This is how we ought to derive. So by applying the boundary conditions. In the similar fashion, we will be deriving h2, h3 and h4. Applying this is to derive h2. This will be using to derive h3. This will be using in order to derive h4. Let's see. Sorry. To find h2. Okay. At node 1, xi equal to minus 1, h2 will be equal to 0, dou h2 upon dou xi equal to 0. You will be getting similar expressions, but only the position of 1 will go on changing. So when you substitute these values, you will be getting a0 minus a1 plus a2 minus a3 equal to 0. Let me call this as equation A. Then the second equation, a1 minus 2a2 plus 3a3 equal to 0. Let me call this equation B. At node 2, xi equal to 1, h2 and dou h2 upon dou xi equal to 0. When you substitute these in equations 1 and 2, you will be getting equations C and D again. Okay. So again adding a plus C and b plus d, you will be getting these two expressions. Okay. a0 plus a2 equal to 0, a1 plus 3a3 equal to half. Again substitute equation F in equation 2, you will be getting minus 2a2 equal to half, you will be getting a2 equal to minus 1 by 4. So if you substitute this a2 equal to minus 1 by 4 in this equation E, you will get a0 as 1 by 4. So now again using equations E, now again using equation C, that is this equation, substitute the values of a0, a2 and a1 from this expression as half minus 3a3. When you substitute these values, you will be getting, when you simplify this, you will get a3 as 1 by 4. Then once you get a3, substitute that in equation F, and then you will get a1 as 1 by 4. Then once you get the values of a0, a1, a2 and a3 and a4, substitute all the values in equation h2. Then you will get, that is not equation h2, it is equation 1. So in place of h we will be writing h2. So you will get h2 as half, sorry, no, not half, h2 equal to 1 upon 4, 1 minus xi square plus xi cube. In the similar fashion we will be doing it for h3 at node 1, xi equal to minus 1, h3 and dou h3 upon dou xi equal to 0. When you substitute this in equation 1 and 2, these are the two equations you will be getting, a and b. Then at node 2, xi equal to plus 1, h3 equal to 1. You can see first this was h1 was 1, then dou h1 upon dou xi was 1, then dou h2 upon dou xi was 1. You should go on applying all those boundary conditions which are given in the table there. You will be getting the similar expressions, but the values will change. The equation slight change will be there in the equations. So you will get equations C and equation D when you substitute these boundary conditions. Again adding a plus c and b plus d, you will be getting a0 plus a2 equal to half, a1 plus 3a3 equal to 0. So again when you substitute f in b, we get a2 equal to 0 and then a0 equal to half. Then when you substitute a0, a2 and a1 equal to minus 3a3 from equation f in equation c, you will be getting a3 as minus 1 by 4 after simplifying this. Again when you substitute back a3 here, you will get a1 as 3 by 4. So substitute all the values of generalized coordinates back in equation h3, you will get h3 as 1 by 4, 2 plus 3 xi minus xi cube. Then lastly to find h4 at node 1, xi equal to minus 1, h4 and dou h4 upon dou xi equal to 0. These are the two equations when you substitute these boundary conditions in equation 1 and 2. And at node 2, xi equal to plus 1, h4 and dou h4 upon dou xi equal to plus 1. So when you substitute these values, you will be getting equation C and D. So D will be a1 plus 2a2 plus 3a3 equal to 1. Add equations A plus C and again equations B plus D. You will get equations E and F. When you again go on simplifying, substituting F in equation B, then you will get a0 as 1 by 4, sorry, a2 as 1 by 4 and a0 as minus 1 by 4. Okay. Then again substituting a0, a2, a1 equal to, that is from this equation, half minus 3a3 in equation C, we will get a3 as 1 by 4 and then we will get a1 as minus 1 by 4. Substitute all these values, we will get h4 as 1 by 4 minus 1 minus xi plus xi square plus xi cube. Let me write this in matrix form. Instead of writing it in horizontal, by representing T here, which indicates transpose of a matrix, we will write all these expressions. So you can see this is H1, this is LE by 2 H2, which is equal to N2, this is H3 and this is H4, LE by 2 H4. So H1 will be equal to N1, but H2 will be equal to, H2 will not be equal to N2, okay, because LE by 2 is present here. LE by 2 H2 will be equal to N2, okay, when you are converting it from global coordinates to natural coordinates. H3 is equal to N3 and LE by 2 H4 is equal to N4. So this are the shape functions for beam element in terms of natural coordinate, which we call it as Hermite shape functions. Thank you.